with that, I'll hand this over to our first speaker, Elisabeth. Elisabeth, take it away.
Thank you, Caroline. I will share my screen. All right, can everybody see that?
Yeah, we've got it. Thanks.
Awesome. So before I start, I'd like to acknowledge that I am presenting today on the territories of the Mohawk Nation, which is the present city of Montreal. And there's a lot to say with how we relate to the land, especially us working in the construction industry. I am learning a lot from this city that originally was First Nation territory and has turned and transformed into a very multicultural and cosmopolitan hub. A little bit about me and CarbonWise. I've worked in the energy efficiency field for years. And I noticed that a lot of people were having a hard time figuring out energy code changes. And I don't blame you, it's hard to follow. Energy and carbon codes are evolving quickly, technology and building practices as well. And I know it's hard to keep track, but we have net zero goals and there's only a path forward. So I feel pretty safe in this room today to say that we can build and renovate better. And that's why CarbonWise exists, and that's why I'm speaking to you today. So I will be talking about a case study of a net zero renovation in the district of North Van we performed the case study earlier this year. This home is still in reconstruction. And we will be updating the numbers from the case study, hopefully with the as-built results either end of this year or early next year. So CarbonWise was hired to investigate the life cycle benefits, both in terms of operational and embodied emissions of this net zero renovation. And we wanted to compare those results with what would have happened if any other homeowner that was not so keen on reducing their carbon footprints would have probably bought this property and demolished the home and just rebuilt a brand new home. So we were lucky to have very keen homeowners wanting to reduce their carbon footprint and willing to make changes to their original plans to achieve that goal. And so we got carried away a little bit, and instead of 2 scenarios, we actually had 4. So the first one was a new home. So looking at a new home built using conventional practices. Second one would be that same new home, but with the addition of the solar panels to bring it to the net zero standards. Third one would be to retrofit the home and reuse and recover some of the materials. And finally, our case home is the retrofitted home with the addition of solar panels to reach the net zero standards. So here are the operational and embodied emissions for those 4 scenarios in tons of CO2 equivalent. The new home would have been using a heat pump, and that would have used about 11,000 kilowatt hour per year, which is 0.135 tons of CO2e per year. This is very minimal. This would have been a all electric home, and thanks to the clean grid we have in BC, that's why this number is really low, and with an embodied carbon of 36.2. Now, if we look at that same new home and add solar panels, then the operational emissions is virtually 0, but the embodied emissions go up 13%. Now that's home. If we retrofit that home, reuse some of those materials, we achieve approximately the same operational emissions, but a 22% reduction in embodied emissions. And finally here, our case home. So again, operational emissions 0, and then plus 17% of embodied emissions from the retrofitted home due to the solar panels. So why those differences? The life cycle assessment of the new build scenario showed us that the roof and the foundation were the most impactful elements. So the roof was nearing the end of its end of life anyway. So in all scenarios, we would have need to be replaced. So there were not really any savings there. So then what was most significant was the slab and the foundation walls, where the reuse provided the largest and easiest carbon savings, as you can see here. So there's no surprise here. Concrete usually represents, between 30 and 40% of the embodied carbon in a new build. So that's where there were a lot of savings. And little story about actually the slab. When we did at the beginning of this study, we got those numbers, and while we were working on this, the homeowners decided to add a bit more to the scope of the renovation, which has then triggered kind of some new construction requirements from the district. And the district came back to them asking for them to pour a new foundation. And, wanting to, keep going with their vision, the file actually went up to BC Housing, and they showed the report, and they showed that we could save up to 8 tons of CO2 equivalent by keeping the slab. And the good news is that BC Housing approved this file so that they could keep the slab. Obviously, it had been approved by an engineer. This is the good news of this project, is that even though at some point we were all scared they would have to pour a new slab, we actually, the numbers showed BC Housing and the district that it wasn't necessary, and all the emissions associated with new slab were definitely not necessary. So that's a good news story. So now let's look at those emissions over time. So first, this is just 10 years. In black, this is the existing home. So that is based on the energy model that was done on the existing home before deconstruction. In beige, the first line above is the new build net zero scenario. In orange, the new build. In red, this is our case home, the deep retrofit net zero. And in blue, the deep retrofit without the solar panels. So the first conclusion here is that the embodied carbon invested in upgrading the home, either through a deep retrofit or a reconstruction, can be paid back in 5 years or less. So in other terms, it takes 5 years or less to see the return on embodied carbon savings, emissions. Now let's look at this for 140 years. And the second conclusion here is that the case home, the red line, becomes the least emitting home at year 35. And why is that? And that's because the retrofitted home doesn't have the power, the solar panels, and that's the blue line. And so it will still emit a little bit of operational emissions over time. So here we can see that it takes 35 years to see the return on embodied carbon investment for the solar panels. Here are some more graphs showing the total embodied emissions and the embodied emissions intensity. In our case home, circled in orange here, we save about 8 tons of CO2 when the home is deconstructed and renovated, and that's the equivalent of the annual emissions of 2 cars. So taking 2 cars off the road. And on the right, this is the embodied emissions intensity, and our home here is at 120. So how does that compare with other numbers from other studies? So those are the results from 3 studies done by Chris Magwood, one in Vancouver with 13 homes, one in Nelson and Castlegar with 34 homes, and the biggest one in the Toronto area. In red are the highest numbers from those homes. And they go from about 300 to 500 kilogram of CO2e per square meter. Again, we are talking about intensity here. The average results are between 150 and 193. This is pretty consistent across the studies, and the lowest results go from 72 to 138. And our home is at 120. So you've probably heard from Caroline about the near zero program from the city of Vancouver, which has the benchmark currently at 200. So our home would then show a 60% reduction from that 200 benchmark. Here is another cool graph. Not much to explain here, except that by reusing the slab, the roof then becomes the #1 emitter. So what else can be done to reduce emissions further? So we looked at the top 3 emitters, and we made substitutions for the roof, windows, and insulation. There are more details in the report, but what I want to show you here is that embodied emissions reductions can be easily achieved by selecting low carbon materials that are available in the market. And so a typical use for a home like this, so any other homeowner probably would have done a lipstick reno and maybe change that natural gas furnace. And so with the emitted carbon of that home, it would take 20 years to match the embodied carbon of 4 new net zero homes. And some other conclusions from the case study. We saw that yes, addressing operational emissions through energy efficiency measures is necessary. Obviously, that number, 5 years payback, is very important. Yes, switching from fossil fuel heating to electric is a great idea because we have a clean grid in BC. Yes, deconstructing and reusing materials, especially the concrete slab, have a big impact. And no, not all materials are made equals. And by selecting, there are low carbon materials available right now that can be selected and can achieve significant embodied carbon reductions. So yes, achieving 50% plus reduction in embodied carbon is achievable with careful material selection. That is it for me. I think I'll keep the questions for the end, but feel free to also get my contact details and reach out if you have any questions. I will post the link in the chat where you can find and download the study on our website.
Thank you very much, Elisabeth. Yeah, let's save questions till the end. So with that, we can hand this straight over to Zahra and Javaria.
Hello.
Hi there. Zahra might not have heard us, or might have.
Yes, no, I did. I'm just sharing my screen, so Javaria will start, and then I'll follow after her. Just one moment while I share my screen.
Thank you.
Okay, do you see my screen now?
Yes,
Yeah.
we got
Great.
it.
Okay.
Great. So, hi, everyone. Me and Zahra are presenting our study. A little bit of background. Zahra used to work with us a little while ago. So we worked together on this study, and now she has moved on to the city of Vancouver. So we're presenting together because she was the lead on this for a lot of the work that we did. The study itself was done in partnership with CSA, with Mantle Developments, which is where I work. My background is architecture design. I've been working with Mantle for a while now. So we'll essentially tell you what Mantle is and what we do, and then we'll move on to the actual study. So Mantle is a climate smart building advisor that helps with projects that go beyond energy and efficiency And we've been working with resilience, life cycle assessment. We also do net zero carbon ready projects, and then target setting for a lot of the clients that we work with. Embodied carbon essentially in LCAs is our bread and butter, but we have other services which are based either with embodied carbon, climate resilience, low carbon construction, and then policy development and research as well. Because we are at a CLF event, I'm not going to go too deep into why embodied carbon is important, but just a rough sort of background. We're looking at whole life carbon. So that's operational plus embodied carbon, essentially manufacturing, transportation, installation, and then operational, which is use, and then end of life. We know that operational carbon has been making great developments in terms of reducing the impact. So I think the way the market is headed, operational is on the downward trend, and embodied is where the focus needs to be moving forward. The new buildings that are coming up are increasingly energy efficient, and the embodied carbon in, say, a 60-year lifespan of a building becomes the more important part of this conversation. When we look at embodied carbon, we're looking at building materials. Zahra, can we go to the next slide? And then in terms of that, we know that this is not a circular process where we're at the end of life, we're usually looking at a product that is being thrown out, and it is not a closed loop. So the study that we're gonna present, so a sort of essential solution to that is to look for reuse. And when we're looking at reuse, we're trying to look at it at a building scale. So when we're looking at reuse, we're looking at renovations, deep renovations, instead of getting new building materials or minimizing the new building materials that go into the work and construction sector right now. The study that we're presenting today stems from the Circular Economy Leadership Canada's agenda to advance circular economy practices in the real estate sector and understand the value of GHG to reach their reduction targets. So they wanted to understand the business case and some key decisions in terms of investing in tearing down or building a new building. Their partner in this was CSA. So with CSA, essentially, there were two studies that were running in parallel. One is the study that we're presenting today. The other was a study by Helen Goodland that was titled Opportunity to Apply Circular Strategies to Existing Office Buildings. I'll share the link for both studies in the chat. The other study was a little more qualitative. So they were looking at the practical issues of a retrofit. The study the Mantle did was looking at the quantitative aspects of a retrofit. So the Mantle study is based on a literature review and then cases for an LCA and how that plays out. A little bit of an overview of the actual study, carbon emissions and circular economy, and how that would lead to Canada's net zero targets. A little bit of a methodology on how we did the literature review and how the case studies came about. And then there is a results and discussion section if anyone is interested in the actual report. In terms of the literature review, the study compares the whole life carbon impact of deep retrofits with demolition and new construction in the Canadian commercial office buildings. The study focused on research gaps on LCA and on circular economy and assessed the whole carbon benefits of a deep carbon retrofit and a demolition. And then we assessed the availability and gaps in the data, tools, standards, and guidelines to conduct these LCAs. What we saw was that there's not a lot of information out there where circularity and LCAs intersect. So we had to reach outside of Canada for a lot of the case studies that we looked at in terms of the literature review. Another thing that we saw is the same intersection does not exist with a lot of the standards. So we looked at a few CSA standards, ISO standards, some of the international European standards. The end of life is not part of any of the North American standards that we looked at, but it is coming up in some of the European standards. So So this is the sort of the list of standards that we looked at. In our study, while some of them acknowledge the embodied carbon benefits of the circular economy, they do not provide any direction on how to assess the embodied carbon reduction. So that's a little bit of a gap. I will hand this off to Zahra to talk through the actual cases and the LCAs, and then we'll talk about the results and the discussion that came off of it.
Thank you, Javaria. So I will move on to talk, maybe I'll just give a quick intro on me. So as Javaria mentioned, I used to work with Mantle developments for the past 2-3 years, and I was the lead on this study, and that's why I'm presenting on it right now. I work at the City of Vancouver as a senior planner and focus specifically on embodied carbon policies and regulations. Again, like this is a previous study, but we at Mantle put a lot of effort into it, and it seems very relevant and valuable to the CLF community. So that's why we wanted to share it. What I'm focusing on is the actual study. So as Javaria mentioned, we did a literature review. The literature review informed a lot of our methodology to conduct the LCA. There was a lot of challenges to run this study because of the data challenges in getting the data, and I'm sure in this group a lot of you are aware on the challenges of getting data for LCA. So what we did was we narrowed down this study to office buildings, and that was mostly because of the interest of the carbon leadership, carbon leadership Canada. I think I'm missing one of the words, but so basically, Circular Economy Leadership Canada, that's the group. So they were more interested in the retail or office real estate buildings. That's why we narrowed it down to this typology. So we took two buildings, one mid-rise office and a high-rise office. So the base buildings were actual buildings that Mantle had done LCA on them on previous projects. But then we did a hypothetical analysis of demolition and new construction of those buildings compared to retrofits. And we also did this study in 3 cities in Canada to assess the significance of the location. So that's mostly the electricity grid. So we had Toronto, Vancouver, and Edmonton. All in all, it will be 12 LCAs. And then in terms of this scope, again, as I mentioned, the actual reference buildings are located in Toronto, but we got some information to modify it for BC and Edmonton context, Vancouver and Edmonton. In terms of the life cycle stages, we included the beginning of the building life. So that's demolition and removal of the existing building for the demolition and new construction, and for the retrofit removal of the elements that will be replaced. And as Javaria mentioned, we looked into deep carbon retrofit, which means replacement of the envelope, mechanical system, and the majority of the interior elements. And again, like we included that beginning stage, and we also included all the life cycle stages after. So when the retrofit building or new building will become operational. The elements that we included the structure, envelope, mechanical, electrical, plumbing, interior, and finishes. And this again is based on the best available data that we had. So some of the data might have come from the actual building, but if we didn't have the data from the building, we replaced it by best available data, either from previous project or similar project. We actually got help from Perkins and Will and also City of Edmonton on some specific guidance on the envelope and the mechanical systems in Vancouver and Edmonton. We assume the same lifetime for both buildings, retrofit and new. A lot of the case studies that we saw in the literature has taken this approach, except for one, which actually done a very interesting analysis on assessing the impacts of the lifetime, but that's a separate topic. Happy to dive into it later on. And then in terms of the elements lifetime, we assume the defaults from the one-click LCA tool, which was the tool that we used, but we also substitute some of the major elements, specifically those that we knew it will be replaced, and in the default one-click LCA, they weren't replaced. So mechanical, interior, envelope, and we got those lifetime expectancies from a study or a brief report from CLF, the CLF from the University of Washington. It's a 2018 publication. And then for the modeling, we did the embodied carbon and refrigerants using the default values of the one-click LCA. And for operational carbon, we assume the minimum performance from the building code of each region. So for Vancouver, that will be Vancouver building bylaw operational carbon or embodied carbon. Oh, sorry, operational carbon requirement. So jumping into the results, as I mentioned, this study does the 3 cities. I'm going to jump into the Vancouver one as it's more relevant to the audience here, but the actual report has the results on all the 3 cities. So just quickly, these graphs, the one on the left shows the demolition and new construction, and the one on the right shows the retrofit for the mid-rise office building in Vancouver. And the gray is the embodied carbon, the dark blue is refrigerants, and the light blue is the operational carbon. So we focus on 2 milestone years, so 20 for climate carbon or climate change targets, so 2030 and 2050. So we saw that at the 2030 mark, Vancouver has, the retrofit has 70% reduction, and by 2050 is about 60% less than if it was built, demolished the existing building and built new. And then this is the same results for the high rise. The high rise results showed less reduction. A lot of those assumptions depends on the material. So there were some variations in the envelope system, and there was some variations in the refrigerants and mechanical systems. So again, still significant. By 2030, about 45%, and by 2050, about 30% less than if it was built new. This is a breakdown. So this graph is the breakdown of only embodied carbon. So here we have removed the operational carbon and refrigerants and only showing embodied carbon, comparing on the left the demolition and new construction, and on the right the retrofit. So what is, and this graph is specifically for mid-rise Toronto. And it's because the actual buildings were in Toronto, the deep dives we did were mostly on Toronto buildings, but they are very similar. So not much difference between the regions. So we just thought that represents the findings anyways. So what is significant here, this is a breakdown of the embodied carbon by the life cycle stages. And as you can see, the dark blue one on the left, this is the production, material production for the new building. And then the light grayish blue one is the use phase. So this is basically the repair and replacement and renovation. So you see that in the new construction, the majority of the emissions come from the first stage, but obviously for retrofit, because we are saving the structure, that becomes way less significant. And this is the same results broken down by building elements, so foundation, floor, roof, envelope, interior, mechanical, electrical, and plumbing. And again, each element is shown for retrofit compared to demolition and new construction. And what I wanted to highlight here is that, as you can see, in the floor, column, beams, and stairs for new construction, concrete is very significant. So this graph shows the elements and material breakdown. As you see, because we are using a whole new structure, the concrete obviously is very significant. But two other interesting or significant things to note is that the systems that we used for deep retrofit and new construction weren't much different, But you see that in the retrofit now, the majority of emissions are coming from the envelope and mechanical systems. So that is something to have in mind when a retrofit is done. We did a few like sensitivity analysis just to see how the results of the retrofit can be less. So this graph shows the base. So the dark blue on the left is the result of Toronto Mid-Rise retrofit building as the baseline. And then we started assuming some changes. So we assumed some salvaging and reusing of the existing elements. So again, these are, so the big study looks into retrofit as a whole, but this is just an exercise to see other circularity practices like the reuse and recycling and of the elements, how much impact they can have. And again, so it's a stepped reduction. So on the as the first test is we assumed salvaging and reuse of some of the elements. We assumed higher recycled content for some of the elements as the next one, which shows like about 6% reduction. And the last test was reducing material use, so more efficient system design. This is a hypothetical analysis. It's not based on actual design, but just to test the significance of it. And as you see, all in all, it may result in about 17 or less than 20% reduction. Quite significant, meaning that if we are doing the retrofit, we might want to still have in sight all the elements, reuse and recycling practices. This graph is another exercise looking into, so the orange one shows demolition and new construction, but this time we are comparing because the actual building was built with concrete, the mid-rise office building in Toronto. But this time we wanted to see what happens if we consider the replacement of that concrete building with a mass timber building. Would retrofit still compare if basically we are not using a new structure? So the gray bar shows the mass timber new construction and the dark blue shows retrofit. So on the left, we are showing the embodied emissions, as you see, and we still see a significant reduction if it's retrofit compared to mass timber. So the mass timber shows 600 per square meter, and the retrofit shows 444. But then another interesting thing is now if we assume the emissions from module D, which is reuse and recycling, and also I think in the tool we also assume the biogenic carbon from mass timber. Now the results will be a little different, but there's a lot of so right now a lot of the studies don't include the biogenic carbon because of the challenges for assessing it, but saying that when we get further down there, it's a significant thing to have in mind. Just quickly, just walking through the key findings that we found significant is that we didn't do study of the operational carbon, but a lot of the literature that we looked at based on either academic studies or actual projects, industry publications, show that deep carbon retrofit can have very close performance to new construction on the operational carbon side. And of course, as expected, and this study that we did, and Elisabeth study showed, the embodied carbon will be reduced significantly. So it's a win-win situation. Depending on the region, again, the overall reduction, so at the beginning of the building life, which we are not operating the building, the reduction can be between 50 to 76% in our study, it was. And then by 2050, which is a milestone climate target, the reduction, again, depending on the city, is about 10 to 60%. And of course, the retrofit, the case of retrofit is much stronger for regions that have clean electricity grid. So of course, BC is one of them, which highlights the significance of working more toward it. And if for whatever reason decided for doing the new construction, I think we go to the classic, okay, now how can we reduce embodied carbon? And again, in our study showed that mass timber structure can have a significant impact if biogenic carbon is included. But of course, there's much more to be done on the methodology to be used for the biogenic carbon. A few major gaps that we identified. As Javaria mentioned, there was not a whole lot of studies on retrofit compared to demolition and new construction in our region, or even in Canada. There is like a few studies that are out there, but we had to refer to a lot of like European and American studies to just understand the methodology, again, showing that it's valuable to do more studies on actual buildings rather than this hypothetical analysis. Another thing that we found, an LCA, as you all know, is as good as the tool that is using. So if the data in the tools are not as strong, the results also may be a little bit less strong. And as Javaria mentioned, right now, the EPD standards in North America do not require including the use and end of life stage. So that's module B, C, and also D. The updated European standard mandates including module C and D. So it's pretty important to update those. And for now that we lack data, one thing that can be impactful is to start having a database or consensus-based guidelines on how to assess module B, C, D, like generic assumptions, because a lot of this data is missing, not all, but a significant portion of it is missing in the LCA tools. Another thing is the lifetime of the building. So comparing retrofit and new buildings. But what I would say is that we are talking about the 2050 climate targets. So this is 40 years, 20 years from now. No, 25 years. So basically what I'm saying is that by 2050, a lot of the retrofitted buildings are expected to still last. And even if they live shorter than new buildings, it will be significant in supporting our climate target goals. And then the other thing is a lot of the LCA studies right now exclude interior and MEP elements. But as we showed in this study, if we are looking into retrofit, these elements are very significant, and even for new construction, but more so for retrofit. So it's important to improve the data availability on these elements. And I think that's it, actually. I'm gonna close our presentation here, but happy to start answering questions. I've seen some messages in the chat, but I haven't seen them. So I'm gonna stop sharing my screen and they can start the Q&A.
Thank you. Thanks, Zahra, Javaria, and Elisabeth for really great presentations.